So for the first part of the lab, what we're doing is we're going to create our own standard reduction table. Now, the regular standard reduction table uses hydrogen as the reference cell. So everything on that table is relative to hydrogen. We set the hydrogen half cell to 0. So if we get a positive voltage when we connect hydrogen to a metal, we know that that metal is more likely to be reduced compared to hydrogen. Here we're comparing everything to zinc. So we are going to set up different cells to zinc, so zinc and copper or zinc and silver, and see what the potentials are. If we get a positive value, then that means that that metal is more likely to get reduced compared to zinc. And so we should get values that are going to be different than the values we got for hydrogen, but by the same amount as we go through. So then what we have here is I have a well plate, and inside this well plate, I have different 1 molar metal nitrate solutions. So you can see the blue here, that's copper 2 nitrate. The orange red, that's iron 3 nitrate. We also have a lead, a magnesium, a silver nitrate as well. And then I have a voltmeter. This is how I'm going to measure the voltage. There are different sensitivities to this. So depending on how much voltage I expect the cell to generate, I might change the sensitivity a bit. So for most of these cells, I am going to get a voltage below 2 volts. So I am setting the sensitivity to 2 volts. There is one cell combination where it will detect a voltage a little bit above 2. So then I would set it to the 20 volts. But you'll see what I mean when we get there. And then in addition to my well plate here, I have little strips of filter paper that I have cut. And then one of these wells is filled with potassium nitrate. This is what's going to serve as my salt bridge. So I'm going to dip this into the potassium nitrate and drape it over connecting the 2 cells, and that'll be my salt bridge. And then the last thing I'm going to do in order to detect the voltage is I'm going to use my electrodes here and touch them to the strips of metal that will be inside the different cells. Now, we're going to start with copper and zinc. If you think back to the problems that we did in the notes, I know that if zinc is the anode and copper is the cathode, I will get a positive voltage. And so I want to start there because I don't know whether the red or the whether the black or the red is going to be the anode or the cathode. And so I want to start with the zinc copper combination to figure out which way gives me a positive value. So I have a little piece of copper metal and I have a piece of steel wool. So what I have to do each time is I have to rub off any potential oxidation that has occurred because this metal is exposed to the air. Different metals, of course, oxidize more or less easily, but I need to do this every single time. So now that I've cleaned off the oxidation, I'm going to go ahead and put this into the copper well. And then I'm going to take my piece of zinc metal here. I'm going to do the same thing. I'm going to clean off any of the oxidation that may have occurred. And then I'm going to put this one into the zinc well there. And then I'm going to take my piece of filter paper, and I just have some tweezers here just for when I dip it in. I'm just dipping it into potassium nitrate because, again, that's serving as my salt bridge. So now I'm going to connect these 2 wells via the salt bridge. And then I'm going to hold these on here and I'm going to touch them to the metal and read what the voltage may be. So you want to try to get as much contact with the metal here as you can to the strip, okay? So when I do this, Okay, so right now I am getting a positive value of 0.990, okay? Right now the red is touching the copper. If I switch this so that the black is touching the copper, I now get negative 0.988. So it did drop a tiny little bit, but the sign changed because I've changed which one is the anode, which one is the cathode. Now, again, I want to figure out which one of these is the anode and the cathode. And I know that if it's positive, that means zinc is the anode. So when I touch the red one to copper, the black one to the zinc, I get a positive value. So what that tells me is that whatever metal I use to touch with the black wire, that is my anode. And then whatever one I touch the red wire to, that's my cathode. So now, I would record that number. I'm gonna just dispose of my salt bridge. And I'm going to take out my piece of copper metal. I'm going to leave my zinc metal in here though, because again, I'm testing everything relative to the zinc. So that was my zinc copper. Now let's test zinc and silver. So I have my piece of silver metal here. And again, I'll clean off any potential oxidation. Okay, and so my silver well is right next to it. Now I'm also, let's clean off the zinc one as well, because even just that little bit that the cell was operating at is enough that it could have potentially oxidized. So I've cleaned off the zinc, and then I'm going to take a fresh sheet of filter paper here. Dip that. Okay. And now I'm going to connect the zinc and the silver cell. And sometimes I just kind of push the little filter paper down a little bit using the metal strips. Now I want to be consistent here. Now that I know the black one is the anode, when I test zinc, I'm just going to make zinc the anode for every single one. So I'm going to leave the zinc one attached to black, and the silver I'm going to do with the red wire. So I connect these, and I'm getting a much higher voltage here. So this one is reading at 1.37, okay? So that means there is a greater difference in potential with the zinc and the silver compared to the zinc and the copper, because I'm getting a higher number. So again, you just try to do the best you can, get good surface contact, and then record the voltage there. So as I mentioned, we would do this for every cell combination with zinc, okay? We would test the zinc with the iron, with the magnesium, and with the lead as well, in addition to the copper and the silver. Once we have tested all of those, now what we can do is we can test other metal combinations, and we just want to keep track of which metal we connected to the anode and which one we connected to the cathode. So one metal combination that I want to do is copper and silver. So again, just cleaning it off each time. So put that back in, take our piece of silver. And we have our diagram there. Get another piece of filter paper. And this is just, regular filter paper that I've just simply cut into strips. Soaked there. And so these guys are diagonal from each other, but that's okay. We connect them. All right, now I'm going to connect the copper as my anode. So I'm going to connect the copper to the black and the silver to the red. And so we get 0.422 as our voltage there. So not as large a difference, but that makes sense because copper and silver are closer to each other on our regular reduction potential list. So that means they don't have as high a value. But again, I am getting a positive value when I set the copper as the anode. If I were to switch these, I would get a negative reading. So as long as we just note which one we made the anode, which one we made the cathode, it doesn't really matter. But we just need to make sure we are recording that. All right, now, another one I want to do where we do see a pretty large difference is with magnesium and silver. So have my piece of magnesium here. And this one probably oxidizes the easiest. So that's why I really want to make sure I do a good job of getting off all of it there. Okay, so then I have magnesium in this one here. And then again, let's just in case, clean off the silver. Each time, make sure there's no oxidation that's hindering, good surface contact here. And then we get our piece of filter paper. And we're going to connect them. Now, this one I am going to set it to 20 volts because I should actually get a reading a little bit above 2. So if I set the sensitivity with a maximum at 2, I won't get the correct voltage. So that's why I'm setting it with a sensitivity all the way up to 20, because that way I would get readings above 2 volts. So I'm going to make the magnesium the anode. Again, that's the black. Let's see here. There we go. All right. So I'm getting a reading of 2.04, slightly above 2. But again, that's why we do want to change the sensitivity there. So magnesium and silver, they're pretty far apart from each other on our reduction table. So we do expect a pretty large difference in their potential values. So again, we would just continue this process with all of the other metal combinations, recording the voltage, recording which metal we connected to the anode and which metal we connected to the cathode. Now, for the second part of the lab, what I want to do is I want to make a non-standard cell. Our standard cells are when the concentrations of both components are 1 molar. But what I want to do here is I want to take our 1 molar copper 2 nitrate and I want to dilute it down all the way to 0.001 molar. And then I'm going to make an electrochemical cell with that diluted copper and our regular 1 molar zinc and see what the cell potential comes out to be and compare that to what the Nernst equation would predict the cell potential to come out to be. So in order to do what we call a serial dilution, I'm going to dilute it multiple times. So there are 1 milliliter is approximately 20 drops. And so I want to dilute this by a factor of 10. It's 1 molar right now. So what I'm going to do is I'm going to take 2 drops, 1, 2, and then I'm going to add 18 drops of water. So I have DI water here. Okay. So now what I have just done is I have taken my 1 molar copper 2 nitrate and I've diluted it down to 0.1 molar copper 2 nitrate. I'm going to do this 2 more times. So I'm going to take 2 drops of this, put it into my next test tube, add 18 drops of water. That will then dilute it to 0.01 molar. And then I'm going to do it one more time. I'm going to take the 0.01 molar, take 2 drops of it, put it into my third test tube, add 18 drops of water, and then I will have a 0.001 molar solution of copper 2 nitrate. So once I've done that, what I did now was I took that 0.001 molar copper 2 nitrate solution and I put it in a well next to the 1 molar zinc nitrate solution. I added a fresh salt bridge that was dipped in potassium nitrate, and then I added my strips of zinc and copper metal. I'm still going to keep zinc as the anode, so I'm going to connect the black wire to the zinc and the red wire to the copper. And then I'm going to record the voltage. And so now I'm getting a voltage. It's lower than what I got before. So remember before when they were both 1 molar, I got values around 0.99, 0.98. Now I'm getting a voltage reading of around 0.88. So the voltage did go down, which makes sense because I did dilute the copper 2 nitrate solution. And so I do see my cell potential go down. What I'm going to do in the calculations is compare this measured voltage to what the Nernst equation would predict the measured voltage to be and see how closely those 2 values agree with each other. So for the final part of the lab, what I'm going to do is I'm going to set up another non-standard cell, but this time zinc is still going to be 1 molar, but I'm going to use silver, not at a concentration of 1 molar. That's what's going to make it a non-standard cell. And I'm going to measure the voltage and use the voltage with the Nernst equation to figure out what is the concentration of the silver ions, and then use that to figure out the KSP of silver chloride. So how am I going to do all of that? So what I want to do to start is I'm going to measure out 10 milliliters of 1 molar sodium chloride. And I'm going to add that to a 50 milliliter beaker. And then I'm going to add just 1 drop of silver nitrate. And so silver nitrate, when it comes into contact with the sodium chloride, is going to precipitate out silver chloride. Now, because I have 10 milliliters of sodium chloride in here and only 1 drop I'm going to add of the silver nitrate, we can assume that the chloride concentration, even though yes, some of it's going to precipitate as silver chloride, most of it isn't because there's such a large excess of chloride. So we can assume the chloride concentration is still going to be 1 molar, but we're not going to know the silver concentration. That's what we're going to have to figure out in our calculations. So I'm just going to take 1 drop. Give that a swirl, and hopefully you can see that a white precipitate has formed. So that white precipitate is silver chloride. But remember, there's no such thing as a 100% insoluble salt. So even though almost all of the silver ions have precipitated as silver chloride, there's still always going to be a little bit of silver plus silver ions that are in the solution. And that's what I'm trying to figure out. What is that concentration? So I'm going to pour a little bit of this into another well. And I'm going to add a piece of silver into that well. Again, just cleaning off the oxidation. Right. And then we still have our standard zinc cell that has not changed. That's still 1 molar. Just gonna clean off the oxidation there. And we'll do the same thing. We're going to connect it with a salt bridge that's been dipped in the potassium nitrate. And when we measure the potential, we're still going to set the zinc as the anode. Okay, so I have my voltmeter set up. So I'm going to make the black again connected to the zinc because that's my anode. All right. Sorry, let me just make sure I'm getting good contact here with the silver. Okay. All right, and so we are getting a volt reading of 0.84 volts. So that's what we're going to record down in our data table. And then we're going to use that cell potential, plug that into the Nernst equation to solve for what is the silver ion concentration that's in this cell right now. And then once we have that concentration, and we know the concentration of the chloride is 1 molar, we're going to then solve for the KSP of silver chloride and compare that to the known value of the KSP of silver chloride and see how well those values agree with each other.